Okay, let's unpack this.
Do it.
Today, we are really tearing into a massive technical report, one that claims to have, well, fundamentally tackled one of the toughest trade-offs in large language modeling.
That's right, the quality versus efficiency gap.
Yeah,
Specifically for linear attention mechanisms. It's a big one.
exactly. We're diving deep into Kimi Linear. It's a novel hybrid architecture, and it's designed explicitly to handle the, frankly, punishing complexity of modern LLMs.
Yeah, and if you're out there working on models needing huge context, maybe multi-million tokens or doing long horizon planning or agentic RL.
You know the pain points. That quadratic time complexity and standard attention, it just kills you.
And the key value cache, the key V cache, just growing linearly, it chokes everything at scale.
It makes scaling these things incredibly expensive, sometimes just impossible.
And this paper, well, it proposes a solution. A
Yeah.
pretty compelling one, backed by a lot of empirical data and some elegant technical ideas.
So our mission today is a professional, comprehensive deep dive. We're going into the architecture, the mechanics, the results.
And we're assuming you, the listener, are coming in with expert knowledge, ML, data science, the math underneath. We're not shying away from the details.
No, we're going straight into the weeds. Linear algebra, recurrence relations, the whole thing. We want to extract the core innovation here.
And the headline claim, it's pretty bold.
It really is. Kimi Linear is being called the first hybrid linear attention architecture that's actually proven, empirically, to beat full attention.
Specifically, full multi-head latent attention MLA, and crucially, under fair, matched scale conditions.
That's the kicker, right? They didn't cheat by comparing a tiny model to a huge one. They matched the training scale 1.4 trillion tokens.
A massive undertaking. And Kimi Linear still came out ahead on quality metrics.
That quality parity or even superiority is huge. But then you look at the efficiency numbers.
Yeah, that's where it gets really interesting. They're talking about slashing the KB cache memory footprint by up to 75%.
75%. And delivering up to, what was it, 6 times faster decoding throughput?
6 times,
Yeah.
at a million token context length. That combination, high quality, massive efficiency, that's been the dream, this sort of white whale for efficient LLM research for years now.
Okay, but let's pause here. This raises a fundamental question right away. Linear attention models, they always have this fixed size recurrent state, right? And historically, that's meant they struggle with retrieval, with expressivity over long distances. They tend to forget specifics.
You do, yeah. Information gets compressed, sometimes lost.
So what's the magic ingredient here? What's the core component that lets Kimi Linear make this leap, shifting that quality efficiency trade-off so dramatically?
Well, the paper argues it boils down to one key innovation, Kimi delta attention. KDA.
It's
A mechanism that refines not just how the model learns, but maybe more importantly, how it forgets information within that fixed size memory.
All right, let's dig into KDA then, Kimi delta attention. To really get what's new here, we probably need to walk through the lineage a bit, right? Where did linear attention start? Exactly. At its simplest, you can think of linear attention as modeling this associative memory process as an online learning problem.
Okay.
Standard linear attention, the basic form, is just accumulation. You often see it written as something like CST1 plus GATVT DTC.
So the state S just keeps adding new key value product.
Right. Mathematically, it's like minimizing this unbounded correlation objective. But the key thing is, it's online learning with no breaks. It just accumulates state forever.
Which leads to interference, things blurring together.
Catastrophic interference.
Yeah.
And unbounded state growth. Not practical.
Okay, so that wasn't going to work. Then came DeltaNet. What was the shift there?
DeltaNet was a really important conceptual leap. It reframed the whole thing. Instead of blind accumulation, it viewed the update as performing online gradient descent.
Ah, okay, on a different objective.
Exactly, a reconstruction objective, trying to reconstruct the value via Dinelati's dollar using the state dissolver and the key B dissolver, like FAT12, and taking a gradient step on that gives you the classical delta rule update. CCT, EAST, I beta shokia PTT ST1 plus beta KT VTT1.
Right, so now the state S isn't just accumulating, it's actively correcting itself based on the input key TT dollars. It's trying to learn and stabilize.
Precisely. It forces the model to manage its fixed size state much more effectively.
But DeltaNet still had a problem, didn't it? It learned, but didn't really forget.
That's right. Once an association was learned, it kind of stuck around unless something directly overrode it. Old, irrelevant information could linger.
So the next step was gated DeltaNet. GDN, adding a forget mechanism.
Exactly. GDN introduced a crucial control, a scalar forget gate, alpha dollar, just a single number between 0 and 1.
And the update becomes Zilius Delta T alpha T T ST1 plus beta KT T T T.
Yep, that alpha fidelity acts like a uniform weight decay across the whole attention head's memory. It implements global forgetting.
Giving the model a way to control memory lifespan and reduce interference from old stuff. A big improvement.
A huge improvement. Made it much more robust, especially in noisy, long contexts.
Okay, so that brings us to KDA, Kimi Delta Attention. Where does it refine things further? GDN had a gate, but KDA's is different.
Fundamentally different in granularity. GDN's gate, that alpha, it's a single scalar value for the entire attention head. It's a coarse, headwise decay. One knob for everything.
Ah, I see. KDA changes that.
KDA introduces a fine-grained diagonalized gate. Instead of the scalar alpha, it uses a vector, alpha in 0, 1 decay, and it applies it diagonally. Text dialpha.
So a whole vector of decay values, one for each feature channel in the key dimension dk dollars.
Precisely, which leads to the KDA formulation, equation 1 in the paper. DASTT, text diag alpha, text IST1, plus BT VTTT.
Okay, wow. So that diagonal matrix text, each feature dimension gets its own forgetting rate.
Exactly, that's the core refinement. Channel-wise, independent decay.
So if one channel is tracking, say, a specific entity mentioned way back,
That channel can have a very low decay rate, preserving that memory aggressively.
while another channel may be tracking something transient like sentence structure that's no longer relevant,
That channel can have a high decay rate, forgetting quickly.
it's like moving from a single master reset button to having individual controls for every single memory slot.
That's a great analogy. It allows for much more precise regulation of the finite state memory. This fine-grained control is what they argue unlocks the RNN-style potential, letting it hold on to sparse, long-range dependencies much better than GDN or other scalar decay methods like MAMA2.
That feels like the key to achieving that quality parity with full attention we talked about earlier, precision forgetting.
It seems to be a critical piece of the puzzle, yes.
Okay, so KDA gives us the expressivity through this fine-grained gating. That's the quality side. But expressivity alone isn't enough, right? It has to be fast.
Absolutely, especially for training these massive models.
So how did they make KDA efficient on hardware? These recurrence relations can be tricky to parallelize.
That's the core challenge. You can't train efficiently by stepping through the sequence one token at a time, autoregressively. You need parallelism.
Which means chunking, right? Processing the sequence in parallel blocks?
Exactly. The paper details the standard chunk-wise expansion of the recurrence, equation 2. You basically compute the effect of all the updates within a chunk, say CC, 64 tokens, all at once.
And they use something called the WY representation to compress those updates.
Yeah, propositions 1 and 2 in the appendix cover that. It's a way to represent a sequence of rank 1 updates compactly as matrix products. Standard technique for these kinds of recurrences.
But just having the math isn't enough. You need to structure it so the GPU can actually crunch the numbers efficiently, especially with modern tensor cores.
Right, and the structure that works well here is the diagonal plus low rank, or DPLR, matrix format.
Okay, DPLR, the general form is like CLTD at BTT ST1 plus KT VTT. KDA fits this, with D being that diagonal decay matrix.
It fits the general form, yes.
Yeah.
But here's where things get subtle and really important for hardware.
Ah, okay. What's the issue with just using a general DPLR implementation?
The issue is numerical stability, particularly when you have that fine-grained diagonal decay and you're training with half-precision floating point numbers like bfloat 16, which you absolutely want to do for speed.
Right. Those low-precision formats can cause problems.
They can. Specifically, the division operations needed to combine results across chunks can become unstable. Prior work, like GLA, often had to work around this by computing things in the log domain or adding extra chunking steps.
Which adds complexity and slows things down, negating the hardware benefits.
Exactly. It prevents you from fully leveraging the raw speed of the tensor cores.
So how does KDA get around this? They use a constrained version of DPLR.
Precisely. They introduce a specialized constraint. Instead of having separate $8 vectors in the low-rank part, they tie them both directly to the input key $.
How so?
They set $text $, like before, but then they set tet alpha t and critically $auto alpha t. That little element-wise multiplication with alpha $, and $dollars is key.
And this specific structure allows them to factor things differently.
Yes, it allows them to factor out the decay term text diag, leading directly back to that clean KDA formulation in equation 1. It seems like just algebraic rearrangement, but the hardware implication is huge.
Okay, what's the hardware payoff?
By binding $80 to dollars in this specific way, they constrain the memory update to be symmetrically related to the input key. The structure avoids the problematic division operations that cause instability in the standard DPLR approach with fine-grained decay.
It sidesteps the numerical bottleneck.
Exactly. And you see the result directly in their benchmarks, Figure 2. KDA runs nearly twice as fast as a general DPLR formulation for sequences up to 64K.
Wow, 2 times faster just from that structural constraint.
Yeah. The paper explains this is because they eliminate the need for those extra secondary chunking steps and about 3 extra matrix multiplications needed in the more general case to handle the numerical issues.
So it streamlines the computation, making it fit perfectly onto the half-precision matrix multiplication units.
It's a really nice example of co-designing the mathematical structure and the hardware implementation for maximum throughput. Very elegant.
Okay, we've got the KDA engine, refined memory, hardware efficient. Now, how does it fit into the bigger picture, the full Kimi linear model?
Right, because they didn't just build a pure KDA model. That wasn't the final solution.
No, they opted for a hybrid architecture, using the Moonlight backbone as a base.
Which is an important choice. It acknowledges that even with KDA's improvements, pure linear attention, pure recurrent models, still might have limitations, maybe in very specific long-range retrieval tasks where seeing everything helps.
So they mix KDA with full attention.
Yes, they use an interlayer hybrid approach, which just means they stack layers of different types. They interleave KDA layers with periodic full attention layers.
Specifically, multi-head latent attention MLA layers.
Right, keeps things relatively simple architecturally compared to trying to mix mechanisms within a single layer.
But the big question is the ratio, right? How many KDA layers for every MLA layer? Too much MLA kills efficiency. Too much KDA might hurt generalization.
Exactly. And they ran extensive ablation studies on this, detailed in Table 1.
And the winner was?
A 3-to-1 ratio. 3 KDA layers followed by 1 full MLA layer. That seemed to hit the sweet spot for both quality and computational efficiency.
Let's look closer at those ablations because they're really revealing. They tried higher ratios too, like 7-to-1.
They did. 7 KDA layers to 1 MLA layer. And interestingly, the training loss was comparable. The model learned the training data just fine, but the validation performance tanked. It was significantly worse.
So overfitting to the local patterns, the recurrent KDA layers got good at predicting the next token locally, but lost the global picture.
That's the likely interpretation. The KDA layers might have overspecialized on sequential structure. The MLA layers, being too infrequent at 7.1, couldn't provide enough global token-to-token comparison to ensure robust generalization to unseen data.
Whereas the 3.1 ratio strikes that balance. Enough KDA for efficiency and local modeling, enough MLA for global context and generalization.
Seems like it. Okay, let's touch on some parameterization details. Pretty standard stuff, mostly.
Yeah, it looks like best practices. Key and value dimensions, DKLA, VLAV, both set to 128.
Okay.
They use short-con plus swish for inputs, L2 normalization on query and key for stability. Seems reasonable.
And the decay parameterization, that vector alpha.
They generate it using a low-rank projection. 2 white matrices, 1 arrow alpha, pass through a learned decay function $, efficient way to get a data-dependent vector.
Makes sense. And they also have an output gate.
They do. The final output is gated. MSRU.
Okay, an output gate. Why? And why sigmoid specifically for the activation sigma?
The paper links this directly to mitigating the attention sink problem.
The issue where the first few tokens dominate the recurrent state too much?
Exactly. That sigmoid gate acts as a data-dependent control on how much the KDA output influences the final layer output. It helps dynamically regulate the flow, preventing those initial tokens from washing out later, more important information. They did ablations, and sigmoid worked better than swish or no gate at all, consistent with other findings on attention sinks.
Clever. Okay, that leads us to maybe the most surprising architectural choice, the positional encoding strategy.
Right. They use no position encoding, no row P for all the full attention, the MLA layers.
No row P? No relative positional encoding in the attention layers at all. That feels bold.
It does. Why would they ditch something as standard and effective as row P in those MLA layers? Seems like you'd want that global positional reference.
It's a very deliberate design choice. They are explicitly making the KDA layers responsible for all positional information and recency bias.
So KDA isn't just memory management, it is the positional encoding.
That's how they frame it. They interpret KDA, with its learned gating and delta updates, as a form of data-dependent, multiplicative positional encoding. The transition dynamics themselves encode position relative to the content.
And the benefit of doing it this way versus ropey.
Well, ropey imposes a fixed orthogonality constraint. It gives a fixed global reference. KDA's positional sense is dynamic, evolving with the data. They argue that this makes it more robust and better at extrapolating to sequence lengths far beyond what it saw in training.
Interesting. Relaxing that row constraint could allow more flexibility.
And there's a huge practical benefit, too.
Which is?
By having no P in the MLA layers during inference, those layers can be converted directly into pure multi-query attention, MQA. Very efficient.
Okay. No ropey means simpler conversion to MQA.
Exactly. And it also simplifies the whole training process, especially for super long context. You don't have to mess around with tuning ropey parameters like frequency bases, which could be a real headache when you're pushing into millions of tokens.
So it's a calculated risk on the positionality front, but with significant upsides in inference efficiency and training simplicity.
Seems that way. And as we'll see, the long context results suggest the risk paid off.
All right, theory is solid. Architecture seems cleverly constrained for hardware. Now, the proof is in the pudding. The performance benchmarks.
Yep, time for the empirical results. And crucially, they benchmarked Kimi linear against the full attention MLA baseline and also a hybrid using the older gated deltanet, GDNH.
And all trained on that same massive 1.4 trillion token recipe. So a fair comparison.
Very fair. Let's start with the synthetic tests. These are designed to torture the model's memory.
Right. Things like palindrome, associative recall, tasks that really test if the model can store and retrieve specific information accurately over distances.
And KDA came out on top consistently. Highest accuracy across palindrome, multi-query associative recall, MQAR, and the stack task.
And this held up as sequences got longer, right? From 256 up to over 2,000 tokens.
Yes. But maybe even more telling is the convergence speed shown in Figure 4.
What did that show?
KDA converged much, much faster than the GDN hybrid on those recall-heavy tasks like palindrome and MQAR.
Why would that be?
It goes back to the fine-grained gating. KDA's channel-wise decay lets it quickly identify and stabilize the crucial memory components needed for the task while aggressively forgetting the noise.
While GDN, with its single scalar gate for the whole head, is just less precise. It can't forget noise without also potentially weakening the signal.
Exactly. It confirms that the precision of the KDA gate provides a real, measurable advantage in learning efficiency for these memory-bound tasks. It's also worth noting they mentioned Mamba 2, which has multiplicative decay but lacks the delta rule, failed completely on these tasks in their setup.
Interesting. So you need both the delta rule structure and the refined gating.
Sees that way for these specific recall challenges. Okay, moving on to scaling laws.
Right. They looked at MOE models, mixture of experts, activating 8 out of 64 experts. What did the scaling curves show?
Based on fitting those curves, they estimate Kimi linear offers about 1.16 times the computational efficiency compared to the MLA baseline during training.
Okay, 1.16x. Now, for an expert audience, that doesn't sound like a game-changing training speedup, especially compared to the 6x decoding promise later.
No, it's not.
Should we interpret this 1.16x more as confirmation that KDA's added complexity, the gates, projections, doesn't significantly bloat the training cost compared to MLA? It basically trains about as efficiently.
I think that's exactly the right interpretation. It shows quality parity is achieved without a major training FLOP's penalty. That's a necessary hurdle to clear. The big efficiency wins are expected elsewhere.
Got it. So let's look at general performance, pre-training results, Table 3. How did Kimi linear stack up?
Consistently top-ranked. Across the board, really.
General knowledge.
Leading scores on HelloSwag, 82.9, MMLU, 73.8, MMLU Pro, 51.0.
Reasoning task.
Top scores there, too. GSMAK, 83.9, CRUXA VeloCot, 62.0.
So it's not just good at memory tricks. It's a strong general language model, outperforming both MLA and the GDN hybrid.
Right. That consistency is important. It shows the KDA mechanism is robust and generalizable, not just optimized for synthetic tasks.
And this carried over after fine-tuning. Supervised fine-tuning, SFT, Table 4.
Yes, superiority maintained. Highest scores again on MMLU Pro, 67.4, BBH, 69.4, and notably strong performance on GPQA Diamond, a tough reasoning benchmark, hitting 62.1 AG at 8, also led on math benchmarks.
Okay, strong across the board. But you mentioned earlier agentic LLMs, long horizon tasks.
Yeah.
That makes the reinforcement learning results really interesting. Figure 6.
Absolutely. They did RL training focused on mathematical reasoning using an in-house data set.
And the results.
Kimi linear showed clear superiority. better efficiency during training, and importantly, faster and higher improvement curves compared to MLA on both training and test accuracy.
The gap widened as RL training progressed.
It did, which strongly suggests that Kimi Linear's memory mechanism, that KDA state management, is significantly better suited than MLA for handling the kind of iterative reasoning and state accumulation needed in complex long-form generation under RL.
That makes sense. RL really pushes the need for stable, selective memory over long interactions.
So looking at the whole picture synthetics, scaling, pre-training, SFT, RL, you see this consistent hierarchy emerge. Kimi Linear on top, then the GDN hybrid, then the MLA baseline.
It really reinforces their central claim, doesn't it, that the delta rule combined with KDA's fine-grained gating delivers robust expressivity across a wide range of tasks.
Especially excelling where precise management of that fixed-size associative memory is key.
Okay, now we get to the part where these architectures really live or die. Long context performance and critically decoding efficiency.
This is where the quadratic bottleneck of full attention becomes truly unbearable. The problem shifts from being compute-bound to being memory-bound.
Because of that massive KV cache, right? It just fills up all the GPU memory.
Exactly. So this is where Kimi Linear needs to shine to justify its existence.
Let's start with quality. How did it perform on long context benchmarks? Table 5, looking at 128K context length.
It achieved the highest overall average score, 54.5, with significant leads on benchmarks, specifically designed to test long-range retrieval, like Ruler 84.3 and Rapokyo 68.5.
Ruler and Rapokyo really probe deep into the context window, so performing well there is a strong signal.
A very strong signal. And remember that comparison to the Ropi variant?
Ah, yes, the version where they did use Ropi in the MLA layers instead of no P. How did that do at 128K?
Substantially worse. It only averaged 51.8 overall.
Wow, okay. So removing Ropi and relying entirely on KDA for positionality actually helped long context performance.
That's what the data strongly suggests. It validates that architectural bet they made. The dynamic KDA-based positional encoding seems fundamentally more robust when you push way beyond typical training lengths compared to fixed Ropi interpolation.
That's fascinating. And they pushed even further, right? The final released model.
Yeah, the appendix mentions the final checkpoint, trained on a massive 5.7 trillion tokens. At a full 1 million token context length, it scored 94.8 on Ruler.
94.8 at a million tokens. Okay, that demonstrates the KDA mechanism scales incredibly well.
It really does. Quality holds up at extreme lengths. Now let's talk complexity and speed.
Let's formalize the theory. KDA's FLOPs per head, sequence length T, chunk size C64, head dimension DL dollars.
The scaling is approximately text KDA 6T D2H plus 3T CDH plus TC222.
The key thing there is the dependence on T, the sequence length. It's roughly linear, right?
Essentially linear in T, yes, which is a world away from full attention's OT2T2DK check. That quadratic term is that killer.
So theoretically, it's much cheaper. How does that translate practically during inference? They use a hybrid strategy.
They do. For the initial pre-fill phase, where you process the entire prompt at once in a large batch, they use that optimized FLOP-intensive chunk kernel we discussed. Maximize parallelism.
But for the token-by-token generation phase, the autoregressive part.
That's where the real bottleneck usually is for long contexts. There, they switch to the highly efficient recurrent kernel formulation from equation 2, just stepping the small, fixed-size KDA state forward, one token at a time.
Okay, smart. Use the best tool for each phase and the speed results.
Pre-filling first. At 1 million sequence length, Kimi Linear showed a 2.9x speedup in latency compared to MLA.
Almost 3x faster just processing the initial prompt. That's significant thanks to that hardware-aware DPLR kernel.
Definitely. But the truly dramatic number is the decoding throughput, the number of output tokens per second, TPOT. That's what determines operational cost and user experience for things like chatbots.
And there.
Up to 6 times faster decoding throughput at 1 million context lengths compared to full attention.
6 times? That's huge. Where does that massive gain come from? Is it just fewer FLOPs in the recurrent step?
That's part of it, but the bigger story, connecting back to what we said earlier, is memory efficiency.
Ah, the KV cache again.
Exactly. Full attention needs a KB cache that grows linearly with sequence length T. At 1 million tokens, that cache is enormous. It swamps the high bandwidth memory, the HBM, on the GPU.
Forcing you to use tiny batch sizes, maybe even just batch size 1, killing throughput.
Precisely.
Yeah.
Kimi Linear, because KDA operates with a fixed size state, dk times dv1, so 128 by 128.2 per head, doesn't have this problem. The state memory is constant, small, regardless of whether the sequence is 1K or 1M tokens long.
So by eliminating that linear KV cache growth,
They free up a massive amount of HBM.
which allows them to run much, much larger batch sizes during inference, even with million token contexts.
Exactly. Where full attention might be stuck at batch size 1 or 2, Kimi Linear can pack potentially dozens of sequences onto the same hardware.
And since the bottleneck at long context is often memory bandwidth, fetching that huge KV cache, increasing the batch size lets you amortize that cost and saturate the compute units much better.
That's the core mechanism. The paper estimates a theoretical 6.3x speed-up potential at 1M context, just from this batching advantage enabled by memory efficiency.
So Kimi Linear effectively turns an I/O-bound memory problem back into a more manageable compute-bound problem. That's the trick.
That's the essence of the efficiency gain at extreme lengths.
Okay, we've seen the KDA mechanism, the hybrid architecture, the impressive performance and efficiency. Let's take a step back and place Kimi Linear in the wider context of all the work on efficient attention.
It's worth revisiting that positional encoding angle one last time, because it's so central to their philosophy.
Right, KDA as implicit positional encoding.
Yeah, they really argue that linear attention, when combined with this gated delta rule, effectively learns a dynamic, data-dependent, multiplicative positional encoding. The transition matrix itself, with the decay and updates, encodes position relative to the content.
Contrasting with Ropey's fixed orthogonal transformations.
Exactly. They suggest KDA's learned dynamic approach is inherently better suited for extrapolation, for handling positions far outside the training distribution, which seems borne out by those long context results we just discussed.
It's interesting to map the evolution, isn't it, from basic linear attention
Which was fast but forgetful unbounded state.
to methods with fixed data-independent decay like RetNet.
Then moving to data-dependent but still scalar, decay like in Mamba 2.
And now arriving at this fine-grained, channel-wise vector decay with GLA and KDA.
It feels like a clear progression towards more and more precise micromanagement of the recurrent state memory at the feature level, really embodying that idea of compression as intelligence, or maybe selective forgetting as intelligence.
How does this line of work compare to the other main branch of efficient attention, the sparse attention methods?
Right, things like sliding windows or dynamic token selection methods like those in NSA or MOBA architectures.
What's the trade-off there?
Sparse attention's big advantage is potentially very fine-grained retrieval. In theory, they can look back and attend to any specific token, however far back it is, if the mechanism selects it.
But the downside?
The crippling downside is that to do that selection, they generally still need to store the entire key value cache for all previous tokens.
So they don't escape the linear memory growth problem, even if the computation is sparser.
Exactly. They might compute less, but they still need the memory, which makes them practical for the multi-million token scales Kimi Linear is targeting.
So the paper positions Kimi Linear as getting the best of both worlds, overcoming linear attention's traditional retrieval limits via the powerful KDA memory, while completely avoiding the KV cache explosion that plagues both full attention and sparse attention.
That seems to be the core argument, yes. And finally, on the hybrid model design.
They use the simple interlayer stacking, the 3.1 ratio.
Right. They explicitly contrast this with more complex interlayer hybrids, where people try to mix different attention mechanisms within a single layer.
Why avoid those?
Simplicity, stability, and crucially, infrastructure. The layer-wise approach is much easier to implement efficiently in existing training and inference frameworks. Interlayer hybrids can introduce a lot of custom kernel work and system complexity, kind of undermining the goal of a practical, efficient replacement. #tag outro.
So wrapping this all up, what's the big takeaway here? Where does Kimi Linear leave us?
Well, the authors are presenting it not just as an interesting research idea, but as a potentially robust, production-ready drop-in replacement for standard full attention architectures like Transformer or MLA.
A replacement that offers, based on their evidence, superior performance across a range of tasks.
General knowledge, reasoning, even demanding RL tasks.
And combines that quality with substantial, sometimes dramatic efficiency gains, especially at the extreme context lengths needed for what's next more sophisticated agents, long horizon planning model.
Right. To recap the core contributions,
Yeah.
you have Kimi Delta Attention, KDA, bringing that refined, channel-wise memory management.
Then the Kimi Linear 3.1 hybrid design, which leverages KDA to slash the memory footprint, particularly the KV cache.
And third, the rigorous, fair empirical validation at scale, that 1.4 trillion token training run, showing quality parity or even superiority over MLA, alongside those big efficiency wins, like the potential for up to 6.3x decoding speedup.
And importantly, they've open-sourced key components, right?
Yes, they've released the KDA kernels, implementations for popular frameworks like VLLM, and model checkpoints. That's crucial for driving adoption and further research by the community.
Allows people to actually integrate this and test it in real-world scenarios.
Exactly. Which leads to a final thought, maybe a question this work raises for the future.
Go on.
Given this strong evidence that Kimi Linear, with its fixed, small memory state managed by KDA, can maintain such high performance, how far can we actually push this? How much expressive power can we pack into these low-rank associative memories, governed by increasingly sophisticated gating and update rules?
Are we approaching a point where the quadratic complexity of full attention just isn't fundamentally necessary anymore for generalized language modeling, even at massive scale?
Provocative question, right?
Yeah.
This paper suggests we might be closer than we thought to cracking that memory constraint problem that has really dominated the field. Maybe the future isn't just bigger models, but smarter memory.
A fascinating possibility. Definitely something for listeners to mull over.